Okay, balanced chemical equations for the following processes. These are, I think, from the book, from the homework. Aqueous potassium hydroxide, so that's going to be KOH. Reacts with aqueous iron 3 chloride. To form an iron 3 hydroxide precipitate. So it's a precipitate, which means solid. It's no longer aqueous, no longer in solution. And aqueous potassium chloride. Is that balanced? No, we gotta do some work here. So we've got, again, we do our atom inventory here. Because the ions aren't changing, we can keep the ions together. In this case, it doesn't really matter whether you do or not. But on this side, we've got 1 potassium, 1 iron, 1 hydroxide, and 3 chlorines. On this side, 1 potassium, 1 iron, 3 hydroxides, and 1 chlorine. Nothing is shared with more than one compound on either side, so it doesn't matter where we start. So we can start with, let's say, OH. We've got 1 on the left, 3 on the right, so we'll make 3 here. That's going to change to 3 of these and 3 of these. And that means we now have to balance the potassium and I think it's now balanced, yeah? All right, great. Ammonia gas, NH3. Reacts with oxygen, also a gas, to form nitrogen monoxide, NO, and water vapor, H2O. Gas. Okay. Is that balanced? Not quite. Let's look at the atoms again. We've got 1 nitrogen, 3 hydrogens, 2 oxygens on this side, 1 nitrogen, 2 hydrogens, and 2 oxygens on this side. So the only thing out of balance right now is hydrogens. So we've got 3 on the left, 2 on the right. What do we do about that? Two and 3? Yeah. So we can put 2 here and then a 3 here. And then that balances out our hydrogen. That gives us 6 on each side. Let's look at what else it changes. It also changes this to 2 nitrogen, and it changes this to 4 oxygen. So now our nitrogens are out of balance. Let's go back to that. Again, saving our oxygen to last because that appears in more than one compound on the right side. So we've got 2 nitrogens on the left, 1 on the right. That means we can put a 2 here. And that once again changes our oxygen count now to 5. So now everything's balanced except oxygen. We've got 2 on the left and 5 on the right. So what do we have to do to get that balanced? What can we multiply 2 by to get 5? Right, so it'd be like 5 halves, but we can't really do that. So what do we do instead? Yeah, let's double everything else. So instead of 2, 2, and 3, we're going to have 4, 4, and 6. So that's going to change our numbers to 4, 12, but should keep the proportion, so we don't have to rebalance anything that we've already balanced. And now instead of 5 oxygens, we have 10. So we can balance that with a 5 here. We're good? All right. Other key things to note here. Well, one thing, oxygen, remember, is O2, not just O. So that would change the balancing. And then if we were to do further calculations, it could screw us up. So once we get into chapter 4, you might get a problem like this that then also asks you how much oxygen reacts with 5 grams of ammonia. So to answer that question, you have to first get the equation right. You have to get the compounds right. You have to get the equation balanced. And then you go through and do the mole calculation. And if anything gets screwed up in there, that's going to carry through and end up with ultimately not getting the right quantities at the end. So that's why we've got to kind of make sure we get all these steps correct on our way. Okay, naming some compounds. SNO2, what'd you call that? Tin. Yeah, this is tin 4 oxide. FePO4. Right, that's iron 3 phosphate. PO4 phosphate is a 3- anion, so iron has to be +3 to balance it out. HClO3. A little tricky. Anybody get it? Yeah, this is chloric acid. It comes from the ion ClO3-, which is chlorate. Saw some people put perchloric acid. What would that be? ClO4, right? The way I remember those is by remembering the sequence. So it goes perchloric, chloric, chlorus, and hypochlorous. And then remembering that the top one is O4. So then you can count down and say, okay, this one's O3, so it's the second one on the list. So that's chlorate or chloric acid. All right, N2H4, what do you call that? This is now a covalent compound. Yeah, so we might call this dinitrogen tetrahydride. Actually, nobody calls it that, although that is technically the correct way to name this. It's true. Its real name is, it goes by its common name, which is hydrazine. It's a reactive source of nitrogen, oxidizing. I think it's used in rocket fuel and things like that, often known as hydrazine. Okay, find the molecular formula of caffeine based on these elemental mass percents compositions. So what did you do first? I don't have these numbers, so I'm going to assume someone's right and use your numbers. We'll see. This one looks reasonable. So we've got this various percents of nitrogens. What do we do first? Yeah, we're going to assume there's 100 grams, and so that means that we can say that there's this many grams of each one of these. Then what do we do with those quantities? We're going to turn them into moles by dividing by the molar mass of each of those atoms. So 49.48 divided by 12, 5.919 divided by 1, 28.85 divided by 14, and so on. And I think you get something like 4.12 moles of carbon, assuming this person's right, 5 moles of hydrogen. All right, we got some significant figures here. Let's see if we do. Something like that. Does that look right? Remember? So then what do we do to figure out the formula? Now we've got the moles, so now we know the count of the relationship. So we're going to divide, right, by the smallest one. Well, this is actually kind of easy because the smallest one's about 1. So we're dividing everything by about 1, which means they're going to keep about those same numbers. So you're going to end up with C4, H5, and 2O. See where I got those from the numbers here? We divide by 1. Now that's the elemental formula of caffeine. The molecular formula, I believe, is twice that. I'm not sure about that, but I think it's C8H10N4O2. Look it up. Questions? Good quiz? 10 out of 10? All right.
For the first one of the naming them.
Yeah.
How, just for future, how do you tell between if it's if something's bonded to peroxide or just two normal oxygens? What do they have to say?
Oh, good question. Yeah, because O2 can be peroxide, right? And then it would be tin 1 peroxide. I guess in a problem like this, there's not a good way to tell, except to realize that peroxide is a much less common ion.
Okay.
And it usually only comes up in these kinds of things when naming it as an oxide doesn't work for one reason or another. I don't know of a tin peroxide compound. I can tell you that I know that tin only tends to take +2 and +4 charges, but you wouldn't necessarily know that. So I guess I don't have a good way of answering that. So if you called this tin 1 peroxide, I guess I would count it right.
Can it also be tin 2 oxide?
It can't be tin 2 oxide because oxide has a 2- charge, and there are 2 of them. So we need a total of 4+ to balance out those. Yeah. But if you saw the O2 as peroxide, that's a 1- charge, then it could be tin 1, which doesn't exist, but for the purposes of the quiz, yeah. Oops. Okay. Good job, everybody. I'll get those other quizzes back to you. I was hoping to have them back already, but I don't. So as soon as I can. You do have labs here, so you can pick them up at the break. Let's move on. Okay, let's start by reminding ourselves what we were doing last time. This is a problem from the book. For each of the reactions, calculate the mass of the product that forms when 3.67 grams of the underlying reactant completely reacts. These are already balanced equations, and we assume that there is more than enough of the other reactant. So we're assuming that the underlying one is the limiting reactant, and there's more than enough of the other one. So work on these. See if you can find some numbers for these. Let's do the first 2 for now, and then actually, sorry, let's change that. Let's do the last 2, C and D. Let's do C and D. See if you can come up with the answers there. 3.67 grams of the underlying reactant completely reacts. How much product forms? And by product, we mean the solid that's formed right here. On the right side. Got some numbers? All right, what'd you get for C? Anyone volunteer? How much of this do we form? 5.89 grams. Anybody get something different? You got 6? Okay. Thereabouts. Okay, what about this next one then? Anybody get something different? Did we get the same thing? Couple nods? All right. So I don't know the answer, so I'm just hoping this you got it right. But it sounds like we got some consensus here. Yeah, so what we're going to do with these is take that 3.67 grams, convert to moles, do the mole ratio, and then find that product. So this would be another way of describing what word might we use to talk about these numbers. If we're figuring out the mass of the product that forms, what's another word that we've used for that? What is that called? How much product you get, you expect to get. Yeah, so these would be both considered theoretical yields. And then we get some actual yield that we could compare to that to get a percent yield. Okay, great. Let's move on. So we talked also a little bit about limiting reactants. The homework for chapter 4 is up now online, so make sure you're working through that as well as in the book. Let's have another quiz on this stuff. I guess since we've moved our exam to Wednesday, we'll do the quiz on Tuesday next week. Okay. And that'll be on all of chapter 4, so kind of to get ready for the exam, the last check on that stuff. All right, so other things on chapter 4 that we haven't talked about yet that we're going to do today, talk about today and Thursday, are solutions. So we're going to talk about a lot of the same stuff we've already done, just in the context of using solutions and concentration instead of masses. Then we're going to look, kind of use those ideas of concentration to look at what happens when acids and bases react with each other, called titration. We're going to get some practice with that in lab over the next couple of weeks. I guess not next week, but in the second half of the class after that. And then we'll go back to the previous set of notes, which is actually the end of chapter 4, talking about different kinds of reactions. And that gets into, I think, a really important part of the class overall, which is how do you predict reactions? When you put some random chemicals together, can you predict what's actually going to happen? So we'll get that kind of at the end of this chapter. And then after that, we'll have the exam on Wednesday, and then we will move on to chapter 5, which is gases. So kind of change gears completely there. All right. So let's look at solutions. What is a solution again? I don't think I have a definition here. So remind me, what's a solution? We talked about this when we talked about mixtures and things like that. How would you define a solution? You want to give it a shot? I don't mean like an official definition. Just if somebody said, "Hey, what's a solution?" What would you say? Yeah, give it a shot. Something dissolved in water. Okay. What does it mean for something to be dissolved? Anybody? Have you heard that word before? Dissolved? So somebody comes up to you and says, "Hey, what is this word dissolved? What does that mean?" What do you say? Disappear? So just no longer exist? Or you just can't see it anymore? It's like magic. It sounds exciting. Yeah. I have a 4-year-old at home, so these sorts of things actually come up more than you would think because they ask you questions about things that you don't think about, like what does dissolve mean? And, you know, probably everybody here, I could show you 2 things, and I could say which one is dissolved, and you would know exactly what I'm talking about, right? But then when we say, what does that word mean? We don't think about it. So you need to be around kids so they ask you these weird questions, yeah. Yeah, kind of like evenly distributed. So that's a big part of it, that a solution is really a pretty general term describing a homogeneous mixture where particles are evenly distributed through other particles. It actually doesn't even have to be a liquid, although we usually think of a solution as a liquid with some kind of a solid dissolved in it. But it's actually much more general than that. There are solid solutions where a solid is dissolved in another solid. One way we think about that is in alloys and metals, like steel, for instance. Have you seen steel? Like cars are made out of and things like that. What is steel mostly made out of? You know? Iron, but it's not pure iron. It's got all kinds of other stuff in it. Carbon, nickel, depends. There are all different types of steels. There's stainless steels, there's high carbon steels, there's all kinds of stuff. So those are all mixed in, and the atoms are evenly distributed throughout that. So it's really a type of a solution. Yeah.
But don't you have to turn it into a liquid in order to mix it in the first place?
Generally, yes. Yeah. So you have to find a way to mix it in the first place. So at some point, it has become a liquid. That's not always the case. You could precipitate a solution where it would form a solid from some other kind of a reaction mixture. You could do a reaction where the solid solution forms in the course of the reaction. But you're right, you need some sort of a fluid state at some point to actually form that mixture. So we're going to get into all that later. I don't think it's here. Yeah. There's a whole chapter later, and we're going to get into gases, because air is a solution, right? You ever think about that? Air is a solution. The solvent could be considered nitrogen, which is the biggest part, and then the solute is oxygen and argon and all the other stuff that's in the air. Carbon dioxide, of course. So solution is actually a much more general term, but when we use it in this particular chapter, in this particular context, we'll almost always be talking about water solutions. So things dissolved in water, compounds where water molecules have surrounded them inside more water molecules, kind of having this solution where they're held within the water network. All right. So one thing that we were going to talk about is this idea of concentration, right? Which is the amount of chemical present in the solution, the amount of solute present, the amount of the dissolved thing present. That's important because it's not always easy to weigh solutions, and it's not always easy to tell how much of something is in by a change in volume. So in that first lab, which most of you figured out, that volumes of pure substances are not necessarily additive. If you put 5 milliliters of this and 5 milliliters of this together, you don't usually get 10 milliliters because the way the molecules interact with each other is going to change what happens. So you end up often getting less. So if we want to know how much of something is dissolved in water, we really needed a different measurement, which we call a concentration. And you've heard that term, concentration? So I mean, we've kind of dealt with this in lab already, like yesterday when we used our 6 molar HCl, that was a concentration that was telling us how much stuff is in there. So the normal one that we use, we're going to later go through different types of concentrations and how we use different sorts of concentrations. But for now, we're going to focus on what I think is the most important one in chemistry terms, molarity. Okay, so that's moles of solute, so moles of whatever you're dissolving, per liter of solution. Moles per liter. So how many moles of this stuff did you put in the solution to make a liter of solution? That's the kind of question that we're answering here. So moles of solute divided by volume in liters of solution. All right. Note here that this is volume of solution, or liters of solution, not volume of solvent. So that doesn't mean that you take 10 grams of sodium chloride and a liter of water and mix them together. That's not what we're talking about. We're talking about, or 10 moles, we're talking about you take your moles of your solute, you put it in the container, and then you fill the whole thing up to a liter so that the solution overall is 1 liter. See that distinction? We'll look at some other types of concentrations in later chapters where we look at them separately. Okay, so let's do a couple quick calculations of how we would determine molarity of a solution that we made up. So calculate the molarity of a solution prepared by dissolving 11.5 grams of solid sodium hydroxide in enough water to make 1.5 liters of solution. So remember that our molarity is moles per liter. But we're given 11.5 grams, so what do we have to do? Yeah, we need to turn that into moles. We can do that, right? 11.5 grams of sodium hydroxide. And then we're going to change our grams to moles using the molar mass. So we've got 23 from sodium, 16 from oxygen. I think that's 39, and then 1 from hydrogen is 40. Grams per mole. And that gives us 0.288 moles of sodium hydroxide. So when we're making the solution, we are starting with 0.288 moles of sodium hydroxide. Does that mean that the concentration of the solution is 0.288 molar? No, why not? Yeah, because we're not putting that 0.288 moles in a liter of solution. We're putting it in 1.5 liters of solution. So we have to make that correction. So it's 0.288 moles of sodium hydroxide divided by 1.50 liters of solution, which gives us 0.192 molar. Now, molar as a unit is usually given with a capital M. If you look at it in the book, sometimes it's capital M, sometimes it's kind of an italicized M, like an italicized capital M. I usually just make a capital M. The only possible confusion with that is that capital M is also mega as a metric prefix, but since there's no nothing else after this, it's not usually confusing. All right, so that tells us that in any liter of solution, there's going to be 0.192 moles of solute. So we call this solution 0.192 molar sodium hydroxide solution. Technically, we should specify that it's 0.192 molar sodium hydroxide in water, because you can make solutions in lots of other things too. You can dissolve sodium hydroxide in lots of other solvents. But because, especially for our purposes here, we're not really seeing solutions in other solvents, we can just assume that it's water and not specify that here. So we'll do that. If you see a concentration that says something like 0.192 molar sodium hydroxide, you can assume that that's a water solution. Okay, so see if you can try this next one on your own. We've now got 1.56 grams of gaseous HCl in enough water to make a 26.8 milliliter solution. So this one we're going to do the same way, same idea. The only difference is our solution volume is a little bit smaller, so make sure you get that in liters before you do the final division. So see if you can solve that one. Good concentration for this one. So we're kind of got it. All right, we've been sitting for about an hour. Somebody want to get up and take us through it on the board here? You get to write on this fancy new screen that they put in. That's like incentive, I guess. It even moves up and down. See, watch. Ooh. So if you're really short or tall, you could move it. I feel like these are going to break prematurely just from people like me playing with them. So the screen is yours. Who's going to show us how to do it?
I have a question.
Yeah.
Can you have a molarity over 1 or no?
What do you mean?
Like, I might be thinking molarity wrong, but like for the answer, could it be over 1 or does it have to be a decimal?
What do you mean by over 1?
Like, I got 1.6, and I'm not sure that's right. Okay. So you got.
Oh, yeah, right.
Sure,
Molarity could be
over 1 or
any.
it could just be-
Yes, it can be so greater than 1. I thought you meant like divided by 1.
Yeah,
or
no,
something.
no.
Yes, molarity can be any number depending on
Yeah, just making
what
sure
the numbers come out
percentage
to.
or something.
Yeah. No, it doesn't have to be a decimal. So who's up? Thanks. Oh, here, you can do it on the screen, so it saves. All right, what do you think? Good? All right, thank you very much. Yeah, so you convert the grams to moles, 4.28 times 10 to the minus 2 moles. Divide that by 26.8 milliliters, which is 26.8 times 10 to the minus 3 liters. Or you could write that as 0.0268 liters. So the only thing here is make sure that you convert that to liters before going on, and that comes out to 1.60 molar. So that would be the concentration. What have we made here, by the way? What do you get if you dissolve HCl in water? You know? Yeah, that's hydrochloric acid. So HCl as a pure gas is not hydrochloric acid. That's hydrogen chloride. It's a gaseous compound, really dangerous, not good for you, because whenever it encounters water, it dissolves in the water, and HCl dissolved in water is what we call hydrochloric acid. So hydrochloric acid will always have a concentration, generally in molarity, sometimes in percent, because it is a gas dissolved in water. One of the things that makes it such a dangerous gas is if you inhale it, as soon as it encounters water, it makes concentrated hydrochloric acid wherever it encounters water, which is inside your body. So that's why we don't tend to want to be around HCl gas very much.
What molar does it become really dangerous at? Because if it's low molar, should it not be that dangerous? Or?
Yeah, it depends on the concentration, right? So concentrated HCl, that is the most HCl gas you can dissolve in water, is 12 molar. So that would be, and we'll use concentrated acids, but those are the kind that if you get them on your skin, they can definitely burn you. We use 6 molar, which is half diluted yesterday. That still can burn you for sure. Once you get down into the 1 molar range, again, it can still burn you, but you have a lot more time to wash it off, and it's not really as big of a deal because it's so dilute. So yeah, good question. That's usually what we don't want to work with concentrated acids, but if we have to, we're just careful not to get them on our skin. Now, HCl is not poisonous. Hydrochloric acid is not poisonous. It's just hydrogen chloride ions. But when it is concentrated enough in acid, it can burn you. So it's corrosive. All right. Another way we can think about concentration is about thinking about what actually happens in solution. So let's talk about this compound, which, just for some practice here, what would you name that? CONO32? Yeah, cobalt-2 nitrate. Nitrate is NO3 minus 1, and there's 2 of them, so we need a 2 plus cobalt to balance it out. So we've got half molar cobalt-2 nitrate, which we dissolve in water. Right, half molar cobalt-2 nitrate dissolved in water. What happens to that? Do you know? What happens to cobalt nitrate when you dissolve it in water? Does it just stay like that? It dissociates. It breaks up into its constituent ions. So that means that here you've got, you make it blue because it's blue. Sometimes red too, depending on solvent. So we've got cobalt-2 nitrate, solid. So these solid little chunks. Then we add water. That's water, obviously. That's water. We put it in there, and what happens? The ions break apart. So for every 1 unit of CONO32, we're now going to have cobalt 2 plus ions and nitrate ions floating around. And those are going to be in this proportion of 1 to 2, because those nitrate ions are going to break up. There's going to be 2 of them. When we get into precipitation reactions and types of reactions, which depending on time, we might skip back and do that first before we do the titration stuff. We're going to talk about how you can tell whether or not something is going to break up in solution. But this one certainly does. And so that means that the concentration of the ions may not be the same as the concentration of the overall compound. In this example, let's say we have half molar cobalt nitrate. That means we have 0.50 moles of cobalt nitrate in 1 liter of solution, for example. Okay. So if we have 0.5 moles of cobalt nitrate, how many moles do we have of just cobalt ions? And remember that moles is a count. So the best way I think to think about this is to go back to the molecule. Cobalt nitrate's an ionic compound. It's not a molecule, but we can still think about it that way. If there were 1 cobalt nitrate, just one of them, how many cobalts would there be there? Just 1, right? And how many nitrates would there be? 2. So if we had a mole of cobalt nitrate, how many moles of cobalt ions would there be? Just 1. And how many moles of nitrate ions? 2, right. So we have half a mole of cobalt nitrate. How many moles of cobalt ions are there? Half a mole, right? So this is going to have, so this half a mole of cobalt nitrate contains half a mole of cobalt ions, cobalt 2, and how many moles of nitrate ions? 1 mole, because there's twice as many nitrate ions as there are cobalt ions. So what does that tell us about the concentration? What's the concentration of cobalt ions in the solution? If the concentration of the overall compound is 0.5 molar, what's the concentration of just the cobalt ions? It's actually also 0.5 molar. Let's think about these numbers again. So we've got half a mole of cobalt floating around in a liter of solution. That means there's half a mole of cobalt ions floating around in that liter solution. So half a mole per 1 liter is 0.5 molar, right? Let's write that. So 0.50 moles of cobalt 2 plus in 1 liter of solution is 0.50 molar in cobalt ions. And then we've got 1 mole of nitrate ions in that liter of solution. So what's the concentration of nitrate ions? One molar, right? Let's say 1 molar, 1.0 molar. This thing is a little bit tricky, this idea, because the idea that the ions might have a different concentration from the compound is not necessarily intuitive. And I think the reason that that's difficult is because we like to think of things in terms of mass. And so if you have a certain mass of something, then a fraction of that mass is from this part and a fraction of that mass is from this part. But with moles, it's a count. So if you've got 1 of these things, you've got 1 of this part and 2 of this part, that's going to give you some different concentrations. So to practice this, let's try this next one. So the molarity is expressed in terms of the starting solute before it dissolves. If we've got a solution that's 1 times 10 to the minus 3 molar zinc chloride, that's talking about 1 times 10 to the minus 3 moles of zinc chloride before it's dissolved in a liter of solution. So after it's dissolved, what's the number of moles of just the chloride ions? And notice it's asking for the number of moles in 1.75 liters. So before we get to that, what is the concentration of chloride ions, of just chloride ions? If the concentration of the zinc chloride compound is 1 times 10 to the minus 3, what's the concentration of just the chloride ions? Is what?
Is it the same?
It's not the same.
2 times 3.
Yeah, it's going to be 2 times 10 to the minus 3 because you've got 2 chloride ions per formula unit of zinc chloride. See that? Because it's ZnCl2. So each formula unit of ZnCl2 has 2 chloride ions. And that means that the concentration is going to be twice the concentration of the overall compound. So that said, try to come up with the actual answer to this question. What is the number of moles of chloride ions in 1.75 liters? Not in 1 liter, but in 1.75 liters. What did you come up with?
Yep.
How did you come up with that?
Well, I figured out that you guys said it was 2.0 times 10 to the negative 3 for chloride, right?
Yeah.
And then I just divided that by 1.75.
Okay. Does that work? What do you think? Maybe? Anybody get something different? No? Everybody got this? Let's go through it and see. So you can actually put this together kind of like if you want to stick with the canceling units type thing that we've been doing. Let's look at it like that in case this thinking about the ions having a different concentration is getting a little too confusing. So we're going to start with 1.75 liters of solution. And we want moles, so we want something that gives us liters per mole. In this case, and we have to be really careful with our units here, our concentration is 1.0 times 10 to the minus third mole, and that's zinc chloride per liter of solution. You see that? So then we need another term that will tell us the moles of chloride ions per mole of zinc chloride. So how many chloride ions are there per zinc chloride formula? Yeah, there's 2 per 1. So that's how we get our doubled concentration, right? So you put that all together, you get 2 times 10 to the minus 3 times 1.75, and that should come out to 3.50 times 10 to the minus 3. All right. Yeah, so I think you flipped it with that
Yeah.
0.1 molar to divide. That's why it's good to do it this way. You'll notice that the units cancel, liters cancel, moles zinc chloride cancels with moles of zinc chloride, and we're left with moles of chloride. So that's more of a kind of systematic way to work through. Okay. A really common thing that we do with solutions is something called dilution. What's dilution? It's another one of those words that you don't actually know, can't define, but you would know what it means. Yeah, add water or add solvent in general, right. Decrease the concentration by adding solvent. This is something that's done all the time, not only in lab, but in lots of other circumstances. Certainly if you work in a field like pharmacy, you have to calculate dilutions all the time for different types of doses of medicines in something like a hospital. If you're in other medical fields, you might need to deal with dilutions as well. Even things like the food and beverage industry, you got to dilute out some ingredient to make a particular solution, or you dilute out a concentrate. Even when you're making juice from a frozen juice thing, that's really a type of a dilution. You're adding water to a more concentrated solution to make it less concentrated. And this is really the whole key of dilution calculations and dilution problems, is that you're not changing the moles of solute. It doesn't matter how much water is in there. If you don't add solute, you don't take solute away, you're not changing the moles. And that really simplifies the calculations. You know how many moles you had to start with. You know how many moles you have no matter how much water you add. So we can figure that out. The way that dilutions usually work is something like this example. Suppose we need 500 milliliters of a 1 molar acetic acid solution, and we have a 17.4 molar stock solution. So that's a known concentration solution that we have in stock, and we want to make that more dilute solution. What volume of the stock solution is required? So the question is, how much of that stock solution do we need to get to that appropriate concentration in the final solution without wasting a bunch and making the appropriate amount? So before we do that, let's look a little bit at the glassware and actually the techniques of how we make those dilutions. And you're going to be making some dilutions in lab in a little bit in the future. We know these things already, right? We know what a volumetric pipette is. Yeah, that's this thing that's meant to dispense has one line on it. It's meant to dispense a particular amount very precisely. If you have an even amount and you need to dispense an even amount, like 5, 10, whatever milliliters, then those are great. Volumetric pipettes are great. Most of you did a really good job on that with your experiments. Some of them a little shaky, so you may want to work on your pipette technique if some of your ranges were a little wide. One kind of pipette we haven't used yet, but maybe you've used in the past, is a graduated pipette. That's a pipette that's had a little bit more education, knows a little bit more. Not really. It's a pipette like a graduated cylinder that has graduations on it, has little lines on it. And this is meant to neither suck up nor dispense an entire pipette full, but to somewhere in between. So let's say that your calculation calls for 1.8 milliliters of stock solution. Well, there is no 1.8 milliliter volumetric pipette. So you'd use a graduated pipette, and you'd go from, let's say, the 1 to the 2.8 or something like that. So you'd start at one line and you'd go to the next line, and that would dispense an appropriate amount. So that's what you use if you need fractional amounts. And that's where those green rolly pipetter things, you know what I'm talking about? I don't know what they're called, those are nice because you can carefully control where that liquid level is. They're not as nice as you noticed for the volumetric pipettes because they make it harder to dispense purely by gravity without pushing anything out. Okay, and then the other really important part that we haven't used yet is a volumetric flask. Volumetric flask, have you seen those before? No, it kind of looks like a regular flask, but with sort of a rounder bottom and then a really thin, tall neck, and it also just has one line on it. And just like a volumetric pipette, this flask is used to contain a very precise volume of liquid. So when you fill it up exactly to that line, where the bottom curve of that liquid is right on the line, that means that you have exactly whatever it is, 25 milliliters or 500 milliliters or a liter. You can get really big volumetric flasks and really precisely measure large amounts of solution. So I don't think the actual technique is here. So what you would do to make a dilution is you start with your volumetric flask. Let's say it's a 500 milliliter volumetric flask for this problem that we were just looking at. And you take your 500 milliliter volumetric flask, you fill it with a little bit of water, like maybe half full with DI water, and then you take your amount of stock solution that you need with the pipette, you carefully put it in the volumetric flask with some water already in it, mix it around a little bit, and then fill it up very, very slowly. At the very end, use a dropper or a Pasteur pipette with the little bulb on it to exactly make the solution up to that line. Then you put a cap on it, you mix it up. And that's your exact solution. You can be very precise about concentration when you make a dilution that way. If you get a couple drops above the line, what do? Yeah, throw it out and start over. Because now you don't know the concentration anymore because you've got more water than what the volumetric flask says. So you got to be really careful at the end to make sure that that level comes up to the line but doesn't go over. Okay, so that's the technique. Let's look at how we would calculate it. So what we do is we determine the number of moles that we need and then figure out how many moles what's the volume of stock solution that would have that many moles. So if we need 500 milliliters of 1 molar acetic acid, how many moles of acetic acid do we need? Right now? Can you figure it out just by looking at it, or should we set up the calculation? Yeah, it's going to be 5.5 moles. Let's look at where that comes from. Remember, we want to keep our units consistent. So instead of saying 500 milliliters, let's say 0.500 liters. And we want our final solution to be 1.00 moles per liter of solution. So that means we need 0.500 moles acetic acid. Okay. So how do we determine how much stock solution would have 0.500 moles in it? It's kind of the same calculation, but with an unknown. So we're going to set up that exact same thing. We don't know how much volume we need from the stock solution, so some unknown amount of liters of stock solution. And this has 17.4 moles per liter. And we want that to also be 0.500 moles. So we solve for that by dividing both sides by 17.4. That one I can't do in my head. Comes out to 0.0287 liters, or 28.7 milliliters. So you take 28.7 milliliters of that concentrated stock solution, that 17.4 molar stock solution, bring that solution level up to 500 milliliters, and then you have 500 milliliters of an exactly 1.00 molar acetic acid solution. All right? So let's look at a little shortcut of how to solve that, and then we'll take a break. I don't know if you've seen this equation before, M1V1 equals M2V2. What that is essentially setting these two things equal to each other. So the concentration, you'll notice that on, you'll notice that on this side we have 0.5 moles acetic acid, and on this side we have 0.5 moles acetic acid on this other one. So that means that this the concentration, or the volume times the concentration, has to equal this, the volume times the concentration. In other words, the old concentration and volume times the volume has to equal the new concentration times the volume. And that's because moles stays constant. Moles doesn't change. So another way this is sometimes written, which is probably clearer, is C1V1 equals C2V2, where C is concentration. All right. So here's an example, this problem. What volume of 16 molar, which is concentrated sulfuric acid, must be used to prepare 1.5 liters of a 0.1 molar sulfuric acid solution? So this is our concentration 1, or M1. The original concentration, the concentration of the original solution. The what volume, that's V1, because we don't know what volume, so that's the unknown. And then our final solution is going to be 1.5 liters and 0.1 molar. So that's, whoops, M2 or C2. We plug those into the equation as shown here. Solve for V1, so V1 is going to be, in this case, (9.4 times 10 to the minus 3 liters, or 9.4 milliliters. So that's a really handy equation. It's easy to remember, M1, V1, M2, V2, and it can be really helpful in solving these dilution equations, so you don't have to go back to moles all the time. But you should know where that comes from, because sometimes you need to solve the moles. You don't just need to set them equal and figure out the dilution. So for dilution problems, this is really helpful. This is also helpful for titrations, which we'll look at in a little bit. So let's take a break now, 15 minutes. Then we're actually going to go back to the previous set of notes and look at types of reactions, and then we'll come back to some more stoichiometry if we have time.